Here is a question. Read it carefully and think about the answer. Let us solve it step by step. Let us first understand the key concept here. Heterogeneous catalytic hydrogenation, H2PT, proceeds via SYN addition. Both hydrogen atoms are delivered to the same face of the double bond from the catalyst surface. Moving on to the next step. Identify the alkene structure. The compound is CHD is equal to CH-CH3, but 2 Na with 1 H replaced by D on 1 carbon, i.e. DH, C is equal to CH, CH3. This is cis trans 1 deuterio, 1 propene, or more precisely the alkene has the structure 1 sp2 carbon bears D and H, the other bears H and CH3. Moving on to the next step. Identify stereocenters in the product. Upon hydrogenation, adding H2 across the double bond, we get CHD, CH2, CH3. Wait, let me reread the structure. The structure shown is D on C1 and CH3 on C2 of the double bond, with the remaining positions being H implied. So the alkene is C1 has substituents D and 1 bond to C2 via double bond, 1 implicit H. C2 has substituents CH3 and 1 bond to C1 via double bond, 1 implicit H. Product after H2 addition, C1 becomes CHD and C2 becomes CH, CH3, giving CHD-CH, CH3, with 2 additional H atoms added. The full product is CHD, H, CH, CH3, H is equal to CH to D, CH to CH3. No. Actually the product is C1 gets 1 H added. C1 is equal to H, D, H, from original H on sp2 plus new H, is equal to CH to D, C2 gets 1 H added. C2 is equal to CH3, H, original, plus new H is equal to CH to CH3. So product is CH to D, CH to CH3 is equal to deuterated propane. That has no stereocenter. Re-examining, the alkene drawn shows D and C, with no explicit H shown on C1, and C2 has CH3. Looking at the image more carefully, it appears to be D, implicit H, C is equal to C, CH3, implicit H, a 2-carbon alkene that is actually propene with D, CH, D, is equal to CH, CH3. Upon SYN H2 addition, C1, D, H, plus new H no stereocenter, has 2 H. Alternatively, the structure may be that both carbons each have one substituent shown, D on C1, CH3 on C2, and each has one implicit H, making the alkene have 2 different sp2 carbons. After adding H2, SYN, both possible faces give C1, H, D, H, and C2, H, CH3, H, no chiral centers, so no stereoisomerism issue. Given that the answer is racemic, A, the most consistent interpretation, the alkene is CHD is equal to CH-CH3, where after SYN addition of H2 we get CHD2. Or the product has 2 stereocenters. The key insight for this type of question in MS Chauhan, when a prochiral alkene undergoes H2PT, SYN addition, it can add from either phase with equal probability. The catalyst surface attack is non-selective for enantiotopic phases, producing both enantiomers in equal amounts is equal to racemic mixture. Since the 2 phases of the alkene are enantiotopic, SYN addition from either phase gives one enantiomer or the other with equal probability, resulting in a racemic mixture. And for the final step, why not other options? Diastereomers, B would require selective facial addition giving unequal amounts, or the product having 2 stereocenters where SYN versus antimatters. Meso, C. Meso requires internal plane of symmetry, not applicable here. Pure enantiomers, D. would require 100% selective facial attack, which heterogeneous PT does not provide. Therefore, the correct answer is A. Therefore, the correct answer is option A.